In this video, we're going to talk about a different type of account, where we make regular payments into it. These are called annuities. So it's not just one lump sum to payment at the beginning. We're going to make regular payments throughout the course of the term. So an annuity is a sequence of equal periodic payments. If payments are made at the end of each compounding period, then we call the annuity an ordinary annuity. This is the only type, that we're going to talk about in this class. So always, even if it doesn't say, you should assume that the payments line up with when the interest is computed. So they're always going to line up. And we're going to start by looking at the future value of an annuity. So we're going to start with an example. So we can compute this without a formula because there's not so many compounding periods in this example. And then hopefully we can sort of deduce what the formula might look like. So suppose Elaine plans to put $100 at the end of each quarter into an account with an interest rate of 4% that's compounded quarterly. So notice that the interest is compounded quarterly and she's making quarterly payments. So they match up. It's an ordinary annuity. So we know that our principal is $100, or I shouldn't say that. Our payment value is $100. The interest rate of 4% is 0.04, and compounded quarterly means that the M is 4. So I'm going to start by putting this on a number line. So we're doing this only for 1 year. So this is the 1 year mark, but we're doing it quarterly. So that means we're going to deposit $100 at each quarter, at the end of each quarter. So these are where our deposits are going to come in. So this 1 is actually 4 periods. So it happens to be 1 year. So what we're going to do is compute the amount of money that each of these deposits earned one at a time. So we're going to start actually with the most recent deposit. So if I deposit $100 at the end of the 4th period, and then I evaluate how much money I have right then, this deposit is not going to make any money. So it's going to contribute only $100. So we put that money in and then immediately look at the account. No interest is going to be applied. If we go back to the 3rd deposit, so this deposit was in there for 1 quarter. So the amount that we're going to get, we can use the compound interest formula. So it's going to be the $100 times 1 plus the interest, the interest per compounding period. So that's going to be 0.04 over 4. And it was in there for 1 compounding period. So this is going to be 100 times 1.01 to the power 1. Now if we look, maybe just number these. So those are the periods. If we look at the second one, oops, it's supposed to be in green. If we look at the second one, same idea, but this one is in there for 2 compounding periods. So it's going to be 100 times 1 plus 0.04 over 4 to the power 2. So that's 100, 1.01 squared. Now the first one that we did is going to be in there for 3 compounding periods. So it's going to be 100 times 0.01 to the 3. So then we want to look what happens after 4 quarters. So after 1 year, or 4 quarters, our A is going to be the amount that we earned from each one. So it's the 100 times 0.01. It's all 4 of these things added up. So we made $100 on the first one, $100 times 0.01 on the third one, 100 times 1.01 squared on the second one, and 100 times 1.01 cubed on the third one, or the first one that we did. It was in there the longest. So we could just add all these up. Okay, you would get $406.04. Okay, so we know the answer. But what I want to do is try and rewrite this without needing to do this sum. Okay, so obviously the more quarters we have, the bigger the sum is going to be, the harder it's going to be to compute. So we'd like to compute this another way. So what I'm going to do is multiply by 1.01 on both sides. Okay, so on this side, the left side, I have 1.01a. And on the right side, I'm going to have every term having a bigger power of 1.01. Okay, this is a trick that we often use when we have sums like this. Okay, so then what I'm going to do is I'm going to take these two. Let's call this number 1. Okay, and this formula number 2. So what I'm going to do is 1 minus 2. Okay, so on the left side, I'm going to have 1.01a minus a. And then on the right side, I'm going to have the blue ones minus the purple ones. So notice that the 100 times 1.01 is going to get subtracted. Okay, the squared one also, those are going to go away. The cube one also going to go away. So what I end up with is just the power 4 one minus the 100 by itself. So the sum sort of cancels out, minus the 100. Okay, so then if I pull out an a on this side, I'm going to have 1.01 minus 1. And I can also pull out a 100 here. It's going to look like that. Okay, this thing here is actually just 0.01. So what I end up getting, my a, is 100. Actually, I'm going to move it over a bit so that I can point at stuff. So my a is going to be 100 times 1.01 to the 4 minus 1 all over 0.01. Okay, now the 100 is the payment that we were making, the payment size. Okay, 1.01, this is 1 plus I, so I was 0.01. Okay, so this is I. And 4 was the number of compounding periods, which we normally call n. So this is the form of our formula. So suppose we make periodic payments. Now they're using the payment value PMT. Okay, so the payment that we make is PMT into an account with interest rate R compounded m times per year. After t years, the future value, so this is like, okay, similar to the A, okay, so it's the amount we have after t years, is going to be our payment, PMT, times 1 plus I to the n minus 1 all over I. So this is the formula we use to compute the future value of an annuity. So let's do an example. So suppose that we deposit $1,000 twice per year into an account with 8% interest compounded semi-annually. So we know our payment is $1,000. Okay, the interest rate is 8% or 0.08. And the compounding period is twice per year or semi-annually, so m is going to be 2. Okay, and we're leaving it for, so, and then in part A, we want to know how much is in there after 10 years. So that means t is 10. So we could start by computing I, which is going to be R over M. So 0.08 over 2, which is 0.04. And then our n is m times t, so it's 2 times 10, or 20. Okay, then we can use our formula. So the future value is the payment, so $1,000 times 1 plus 0.04 to the power 20 minus 1 over 0.04. Okay, now if you go straight to the answer here, that is totally fine. You should try not to round too early because it might mess up your amount. Okay, so if you are going to round, keep more than 2 decimal places. So that to make sure you don't lose any information. But you could also just use your calculator. So you can do this all at once. So if you do 1 plus 0.04, okay, this bracket, then you can hit equals. And then you can push to the power, or answer, to the power 20. You can push equals. And then you can do -1, push equals. Divide that answer by 0.04. Okay, that's going to give you the thing inside this bracket. Push equals. And then you can times it by 1,000. Okay, and then you don't have to round ever. If you do round and you want to write down what this is, okay, just make sure that you keep a bunch of decimal places. So like for instance this, 3 decimal places will not be enough. Okay, so I actually need more. I think it's like that. So then when I multiply by 1,000, I'm going to have 29,778.08 cents. Okay, that's my future value. Okay, so you need quite a lot of decimals here, especially when you're multiplying by a big number, because it's going to move the decimal place over a few times. So when you're at the end, you should always round to 2 decimal places because we're talking about money. Okay, so it doesn't make sense to have another number at the end because you can't have half of a cent. Now, how much of this is interest? So how much did we actually deposit? Okay, we want to know how much we actually put in. So that's going to be our payment times the number of deposits. So here that's 1,000 times 20 deposits. So we actually put in $20,000, which means that the interest is our future value minus the deposited amount. So anything that's extra has to be interest. Okay, so this is going to be $9,778.08. Okay, in interest.